Hello, everyone. Good to see you again. I hope you're all doing well. We are currently really enjoying the spring that arrived to the Netherlands over this weekend. And today we are back with another webinar, but before we start, let me make some announcements. As some of you may already know, we opened the registrations for our upcoming physical trainings in Germany in the month of April. We are closely monitoring government regulations, and in case they do not allow us to have a physical event, we will move the trainings online, and we will make the announcement about this mid-March. If anyone is interested, please check out our website, and if you have any questions, you can contact us for further information. On another note, if anyone has any job openings, we'll be happy to announce it on our job Discord channel. Just send us the job description and we'll do the rest for you. Please also don't forget to share your feedback with us at the end of the presentation and give a shout out to Farimah on social media, because it really motivates both her and the rest of the team to deliver such webinars. Today we have Farimah with us, who is an assistant professor at the University of Florida, who will present her research on security property-driven fault injection assessment in modern systems on chips. As usually, today's webinar will consist of a 30-minute technical talk followed by a 10-minute Q&A. I would like everyone to share their questions in the Zoom chat, and we will answer them when the presentation is complete. Without further delay, I would like to invite you, Farimah, to start your presentation.
Thank you, Andrew, for the nice introduction. Hello, everyone, and welcome to my presentation today. As Andrew mentioned, I'm an assistant professor at the University of Florida. That my research involves in developing automated CAD tools for detecting and identifying security vulnerabilities at various levels of abstraction, and finding countermeasures for them. So I work with usually formal methods, semi-formal methods, machine learning techniques to detect several types of attack, from the side channel leakage or information leakage, hardware trojans, and most important, default injection attacks. So in today's discussion, I will go through one of the techniques that we have developed for identifying the critical locations in the design for that they are susceptible toward fault injection attacks. So I hope that my presentation is visible. Yes?
Yes,
perfect.
Everything's good.
So here is my outline of my talk. I'm going to just briefly talk about different techniques of fault injection attacks and some countermeasures. And I'm going to present the SOCs, our proposed framework, and talk about the conclusions and future goals. So as you all know, now is the era of IoT. We have the devices that they are connected with each other. They can think, they can sense, they communicate and act with each other, and they are touching every aspects of our lives, from the smart appliances to the smart cars, smart phones, all of the track changer of our exercises to the smart tattoos. And then, we now we have the concept of smart cities, and by Cisco, predicted that we will have 50 billion IoT devices by 2020. Last time that I checked, it wasn't 50 billion. By the exact number was 43 billion number of IoT devices. So it means that per person, we are having 7 to 8 of those IoT devices. And these IoT devices, as you know, that they are touching every aspects of our life. Because of that, they are they're keeping our financial data, our physical data, health-related data, and more and more. So it was really important for us to be able to protect the security of these devices. So let us look at, what is the backbone of these IoT devices. So right now, most of the IoT devices, they consist of one or multiple system on chips. And here I have shown the full stack of system on chips from the hardware to the custom applications. But we know that the hardware, which is a SoC, this is the most important part that we need to make sure that these are fully protected towards various attacks, because in that location, if we have some errors, it's very difficult to patch them later or address them later, and they are providing a lot of access space to various type of attacks from the higher levels of abstraction and higher layers. So one study at DARPA has shown that by addressing the security vulnerabilities at a hardware level, we can address the security attacks for a whole system by 34%. So it's very important to address these attacks. So as I said that, SoCs, that they are backbone of these IoT devices, that protection of them is kind of it has a one-on-one translation to the security of these IoT devices. Because that they need to support various set of applications, and these applications may be, working with sensitive data, keeping our sensitive data secure. So it may have include a lot of assets, such as, on-device keys, encryption, decryption keys, configuration keys, intro keys, and I'm sure that you know all better than me that there are various sets of attacks that they need to be protected. So, however, we have witnessed a huge array of attacks that they are targeting the integrity, availability, as well as confidentiality of these assets. And so among them, we can talk about power side channel attacks, timing attacks, EM attacks, information leakage attacks, fault injection attacks, and hardware corrosions, and so on and so on. But among all of these attacks, the fault injection attacks are the most important one and the critical ones. Because of that, there are various ways to inject attacks in a design if the physical access is available. And then there are several different tools and equipment can be used, but not all of them are very expensive or out of access of the attackers. So therefore, they are very common. An attacker has shown that by using fault injection attack, they could leak RSA keys, AES keys, and they could actually bypass the security mechanisms of so many security critical IPs and security critical operations. So what are the fault injection attacks? It's that we intentionally inject a fault into the system that facilitate the leakage of assets in the system or bypass the security mechanism. So there are different ways of performing these attacks. We categorize them in three classes. One of them is non-invasive attacks, such as clock glitching, voltage glitching, or EM explosion. We have semi-invasive attacks, such as focus light beams and overheating, and we have invasive attacks. So here, for example, in this example, I have shown fault injection using clock glitching, and in that case, the length of the clock has been shortened by introducing a premature toggling here. Therefore, it will lead to storing the wrong result or bypassing some of the critical instructions in the design, and it leads to bypassing the security mechanisms ultimately. So non-invasive fault attacks, two of them I will talk here. So one of them are most significant ones is clock glitching. So clock glitching can happen, can based on violating the setup and hold time of flip-flops in the design. And then it will end up that the design to latch the incorrect value, or bypass the some of the instructions. And so it's one of the very important ways of injecting attack, because it's very easy to inject attack with this technique. You don't need to, attacker doesn't need to have information about the internal architecture of the designs, and so it's very easy to apply these attacks. At the same time, we will talk about that is not very focused, and these attacks are going to be global attacks, global faults that is going to be injected in the design. So the next one is voltage glitching, that it's based on run the chip based on using a depleted supply voltage, and ultimately what will happen is some of the high threshold transistors in the design will be stay open, and then we're injecting some wrong values in the design, or the design will not work correctly. At the same time, there would be some kind of introducing some power spikes in the design that they will be translated to some currents, and then at the end may be translated to set of violations, and the same fault will be injected in the design. And these are very similar to clock glitching attacks. They are very easy to apply. They are global attacks, and so they are mostly used to change the value of the program counters, or loop on bounding in the design. So therefore, it translates to skipping some of the security critical operations in the design. The semi-invasive attacks, unlike the non-invasive attack, that they do not need any physical change in the design, they are based on some kind of limited hardware change in the design, and they are based on one of the, for example, the technique that we are talking here is based on focus lean beams, or focus light beams, or lasers, that it creates in a PMOS transistor, it creates a hole between electron and between electrons, and it creates a voltage, a current, and that current will be translated to a voltage, and again there would be some kind of voltage pulse in the design, and the value of the certain points in the design can be flipped, either from 0s to 1 or 1 to 0s. And so one of the typical targets of such attacks would be the SRAM bits, that they have shown that they can, some part of the scan, SRAM cells can change their value from 0s to 1s. And there are some successful attacks shown in the academia that, by changing only one bit of the key in AES applications based on, differential fault analysis, that particular bit of the key can be leaked by faulty operation of the design. At the same time, the correct operation of the design and differential analysis can show the that one bit of the key, and that can be repeated to extract some major part of the key. And the last one, that it's invasive fault injection attacks, are based on focus beams, or FIB. That FIB is used in manufacturing facilities for last edits, that it's based on creating some tracing some passes, adding or removing some circuits, or some kind of layers, and kind of making sure that some patches at the last level to address some kind of manufacturing defects. At the same time, attacker can use these technologies, these fit technologies, to insert some traceable paths from the very last metal layer to some kind of internal signals in the design, and then it gives them some kind of exposure to the internal signals that some of them, based on that, some of them may be the critical operations, critical information such as assets in the design. And so they need physical change in the chip. So therefore, there are some kind of delayering and polishing from the backside it should be happen here. But at the same time, they are very focused and they are very precise from the location that the fault is going to be injected. The fault in such cases would be a permanent fault. In comparison with the last two previous techniques that we talked, their faults can be transient faults, and they can be happen at the a kind of specific amount of time. So we show some application of these faults on different design. For example, here we have AES design. That is AES. We are showing the finite state of the design. That finite state usually has 5 states based on one of the implementations that are accessible from open code. And these 5 states starts from the waiting for the key, waiting for the plain text, and it does the initial round of operation, and then goes through the do rounds, and based on the number of rounds, it will stay in this round, and then the final round, the plain text will be completely, converted to a random ciphertext, and then, done signal will be asserted at this state, showing that the ciphertext is ready and it can be read by the output. However, as you can see that this final round is a protected state of the design. It should be protected toward various attacks. A do round also should not be bypassed. For example, if we somehow can, starting from this initial round of the design, go to the skip this do round, and going to the final round, so it means that we are skipping these rounds of encryption, and our ciphertext is not fully encrypted, and it has a lot of information about the key, about the plaintext, and the strength of the whole the AES mechanism can be bypassed. So such faults can be injected by changing the setup time during some valid transitions in the design. For example, if you could see here, from one valid, we have 2 valid states in the design. So from these transition from 10 to 01, because both of the bits are changing during this transition, both of the flip-flops are going to change. So it's possible to violating the setup time hold times to end up to another state, such as 00 states or 101 state. And if you think that 101 state, it shows the encoding of our protected state, it means that by injecting fault during the valid transition in the design, we can end up to a protected state and leak the information. At the same time, we have some don't care states can be introduced based on the synthesis tool while mapping the RTL codes to the gate level codes, and those don't care states. So based on the optimization mechanism that the synthesis tool will use, the don't care states may be connected to some the recent states of the design, or some connected to another states of the design. And we have shown that different encoding will result to different connectivity of these don't care states. And if the don't care states, they are connected to the protected states of the design, such this case that we have shown here. So if we are just doing the regular verification, we cannot find any problem in this design. But however, because that this don't care state has the access, if we can inject the fault during some of the transitions, valid transitions of the design, and we end up in that don't care state, the don't care state, the next clock cycle is protected, is connected to the protected state, therefore the whole security mechanism can be bypassed by these fault injections. Another example would be the example of injecting fault in an SRAM cell. And in this example that you could see that the SRAM has been, divided to 8 distinct areas, and they have shown that, by these optical, beams, so we could actually inject in this area, we could inject flip the 1 to zeros, or stay at zeros. With that, here we could inject based on that, the intensity of that, that laser light, at the same time that the location of PMOS and NMOS transistor. We should show that that a fault can be injected to flip the 0 to 1s, or if the value is 1, it can be injected as 1. So although that it's in current technology is very, very difficult to inject only one fault at the SRAM locations, because that our technology is much smaller than the wavelength of these visible lights. But at the same time, researchers have shown some ways that they could precisely target some part of the SRAMs. So there are various countermeasures have been introduced in the literature and by industry to prevent such attacks. And we categorize them based on 2 classes. The first one is intrusion prevention, that we are using some kind of physical layers or packaging technologies or sensors to be able to detect such faults and prevent them from the happening. And the other one would be the kind of error detections at the architecture level. So they are based on that, mostly based on some kind of redundancies, and that redundancies can be in terms of hardware, in terms of timing, in terms of information. And so the intrusion-based prevention, they are usually, they have the better performance, but they are very expensive, and because of the, you don't know where is the priority for you to cover it based on the, and protect the design against fault injection attack. Usually, people will end up to protecting the whole design, and it translates to a lot of cost and area overhead, and it's not very much applicable to that IoT devices that we are talking about them right now. They should be low overhead. They should be kind of widely applicable. The solution should be widely applicable to all of the designs. At the same time, the error detection techniques, they are they have low cost, but at the same time low coverage, and we will talk about a little bit in detail about those. So one of the intrusion techniques is kind of a complex packages that they have some kind of they based on 3D ICs that is going to be very hard and difficult to target in the inner layers, and they are, they have been covered based on, detection mechanisms, these complex packages. At the same time, we have some kind of sensors that they are kind of sensitive to the change of clock frequency, change of temperature, change of voltage, and kind of any out of range operations, any out of range, physical characteristic will trigger the alarm, and try to just prevent these attacks, detect them and prevent them. One of the most applicable techniques will be kind of protecting the backside using the kind of layer that from the using the PN junctions from the backside to make sure that if there is some kind of it's kind of a current that is going to be leaked, new current is going to be introduced in the design that will be detected. And one of them, the other technique would be kind of frontside active shielding, that it tries to find whether there is a fibbing happens in the design. So what it does is it use kind of testing mechanism. It tries to just create some kind of current in the higher levels of the very last active layers of the design, and see that whether there is a change of in the golden there is a change in the runtime signature of the design with the golden signature that it can get from the lower layers, and based on the comparison of those, it can detect such attacks. So as we said, that they are very, very expensive, and so we don't know which part of the design we need to just apply these countermeasures, and ultimately we may end up just protecting the whole design. The other error detecting and recovering from the error mechanism, they are mostly based on redundancies, and these redundancies, one of the famous techniques would be the voting mechanisms or triple module TMRs, or triple module redundancies, that we just having a voting system and see that which part of the design is going to be has the fault, and we try to, using the voting mechanism, to recover from that fault. And the other technique would be that repeating that of the same operation at different times, and then trying to just has kind of comparison, or making sure that we can recover from temporal attacks. So although that they have low or more manageable overhead, but even that error detection and error recovery mechanism that we are putting in the design, they can be also susceptible to faults, and they do not have very high coverage. So for example, we talk about error correcting codes. The error correcting codes, one of the very, very simple of example of those would be parities, and parities that detect the errors in odd locations, but we miss the errors in the the other locations. And so it has low coverage, and but sometimes even we wanted to just apply such technique, we will end up by having the area of any overhead of 1x, 2x, 3x, or overhead for that part of the design, and still the overhead may not be manageable for IT devices. So I hope that until now I'm convinced that fault injection is a very powerful attack, and so the current countermeasures are not very effective in terms of overhead area timing, and so we really don't know that which part of the design are more susceptible to faults, and to be able to protect them. But at the same time, we wanted to do some kind of analysis to see that what are the most important scenarios in terms of security that we wanted to protect those scenarios, to make sure that fault, if there is a fault in those locations, we can recover from those faults. And if there is a fault in those locations, none of the security mechanism, none of the security properties of the design will be violated. If you find those locations, therefore, the good thing about that would be each of the countermeasures that we wanted to use those countermeasures can be applied locally, because we found, instead of protecting the whole design, we found a few nets here or there, and said that protecting those will lead to protecting all of the security properties of the design, and therefore we we have the higher protection with a manageable overhead. So that was the motivation of our framework. So we developed a framework, we call them SOFI. The SOFI is based on security properties of the design. So what it does, it takes as an input a set of security properties of the design, and then based on the fault modeling and based on the fault characterization that we create, we produce a fault list, we give it to a fault simulator, and we saw that by injecting the fault at different location of the design, is it possible for us to inject any security properties of the design? And if yes, so those parts of the design will be reported as vulnerable locations that it should be protected against these faults, and if not, we are good. So let us just talk about one of those security properties. If you remember that I talked about these, the FSM of an AES, and we talked about that the done signal, which shows that the output is ready and it can be read. So it should be asserted after 10 rounds of operations, AES operations, and then it when the ciphertext is fully encrypted, the done should be 1, and it means that it's secure and that nothing from the plaintext can be leaked. However, if we can manage to inject that done signal after the first round of AES, so what will happen is that, so at that round, we read the key, we just read the plaintext, and then, or even after that, is the wait key or reading the plaintext. So therefore, we can we can infer a lot of information from the key, from the plaintext itself. And that's one of the security properties of the design that definitely should be protected. So it means that the security properties is that during different rounds of operation, none of the states of the design should be bypassed to be end up to the done states, and the done will be asserted while the design is not fully encrypted. And so we will create a set of these security assertions, but our framework assumes that these set of properties by the designer will be given to the to these SOFI framework. And these properties should be kind of in executable format, and at the same time should be relatable to be violated by kind of fault injection attacks. And then our framework tries to see that how many of them can be violated by injecting fault in different locations. So these security properties can be, written or prepared in a Strobe files in system Verilog, that it talks about when, where, and what to check for a security property violation. And we kind of do the differential analysis with the good circuit and faulty circuit, and see that that the fault has a significant effect on the security properties. So to have a comprehensive fault analysis, fault injection analysis technique, we actually create fault models. That is, fault model shows that what would be the result of injecting fault from different techniques, what would be the kind of spatial control we have, what kind of temporal control we have, and fault duration. So based on each of those, our fault list will be different. So now, just based on these categories, we have created a fault model, which is going to be the converting the physical attribute of the fault to a model that can be simulated based on that fault simulation technique. And those be based on, whether that fault is going to be global or local. And so we talked that the global faults like, clock glitching, or local faults can be like that, laser beams. And kind of locations we have a complete control. For example, for clock glitching, we do not have a control, and time, and so on and so forth. So based on that, we have created a fault list, and that fault list, for some small design, we have considered all of the combination of concurrent fault, and for the large design, we consider only at most 2 fault locations. And so based on the faults that we have identified, based on the cone of influence of each of those security properties, we try to we came up with the initial list, which we call them effective faults, that the injecting faults on those locations may violate the security properties. At the same time, to be able to reduce this list, we try to prune it to come up with a critical faults. For example, here that in this design, we have a security property that that net shouldn't be 0 var when all of our inputs on var 1, and if it becomes 0, so it means that that security property has been violated. So there are 7 different combinations for injecting fault at this location, and however, we're just only covering the fault on C or A or B. With these 2 critical faults, we can cover the whole scenarios here. And we have done also kind of fault feasibility analysis based on the fault model that we have. For example, if our fault model is clock glitching, here in this example that I have shown, we have to have a switching between the states to be able to inject the fault through violating the setup times. When we are in different rounds of AES operation, because we are staying at the same state, it's not possible for us to inject the fault to go and to another state. So therefore, we are saying that if there is a fault that if they have wanted to just consider any faults in between these rounds, the 10 rounds of AES, because there is no switching, we are going to just prune them and saying that we don't consider them because they are not feasible. And so we have done our analysis on a set of benchmarks, and we came up with the security properties based on that, the attributes and behavior of the FSMs, the encoding of the FSMs, the don't care states, the transitions, protected state. At the same time, we came up with a set of properties based on differential fault analysis, and in these designs, and said that what are the most important security properties that we should protect the design to prevent differential fault analysis. For that, we have created an internal database of all of these properties, and it's an ongoing effort. All of these properties are going to be added in that database. At the same time, we have done a very thorough literature review. And based on all of these security properties, based on the fault categories and fault locations, so we have shown that for each of those designs, we have identified a very small set of locations, and then we showed that which part of the design need to be protected to fully protect the design to the against fault injection attacks. So our future work will focus on how we wanted to expand this software framework at the different layers, because right now it has been done at gate level. We wanted to expand it at the RTL level and physical layer. And we wanted to just, right now we have done all of our analysis based on power glitching and clock glitching. We wanted to do some kind of comprehensive fault analysis based on different models. And we are going to develop some kind of countermeasures. So not only that those countermeasures that we thought can be applied locally, but there are some other countermeasures that we can consider. For example, if I'm talking about a specific net in the design, and I know that it's susceptible to what one types of the attack. So maybe by just changing different gate type, different characteristics of that transistor, you're changing the weight, width of that transistor. So maybe we could, in a very, very local manner, prevent those scenarios. Now, as part of our research, we're focused on developing countermeasures for any type of these faults. And we wanted to just do the kind of automatically extract all of those security properties to not to be dependent on the input from the design. Thank you, and I will be happy to answer any question that you may have.
Thank you, Farimah, for your presentation. We got a question from Asmita. In practical applications, there are a lot of ongoing parallel processes on SoC. In such scenario, how you locate the exact timing to glitch? Does the analysis using oscilloscope is sufficient to identify the time to glitch, or you perform SCA to do better analysis?
Thank you. That's a very nice question. So it depends on the fault model that we are considering. So there are two ways here. Is that one of the analysis is that if I'm an attacker, I wanted to attack this design. I wanted to detect that where exactly I inject the fault. And I have to do kind of analysis, as you said, oscilloscopes and kind of side channel analysis to find out the exact time that to inject that fault. The other technique that we are doing is that I get a fault model, and based on that fault model, I'm saying that let me see that where that fault is going to be propagated, and what time that fault is going to be propagated, and then let me see that which kind of critical locations in the design should be protected, because if there is a fault injected and those locations, that property may be violated. So the property may be violated. So based on, because now I know the property, exact property, that when what is the target of this property. So I know the cone of influence. I know that some kind of information about the timing, that when the fault should be injected to that fault to be bypassed. For example, that I talked about feasibility analysis of that security property for an AES. So therefore, I can do the fault simulation analysis and saying that, based on this fault model, in these locations, you have to protect them. And the fault model that we have considered here, that would be the clock glitching. So it means that I do not have any control that where that fault is going to be located. I am going to say that, let me think that, at these locations, that which is span of cone of influence of these security properties, exhaustively I'm going to test that based on the fault models, if the design is a small, or based on that some kind of condition, and then let me see that that fault, it can be propagated anywhere in the design. Let me see, I can some of the properties can be violated. I hope I answered the question.
Thank you for answering the question. We have another one from Alexander. He's asking, the fault model you assumed was specified as bit flip. Does that mean only a single transition, like 1 to 0, or does this allow any transition 0 between 1?
Any transition. So it's so a little bit, I need to just talk about that. That fault simulation that it happens, it's based on creating a lot of random stimulus, and it does the fault simulation. And that fault simulation, based on that current value that we have, we think that the value will be flipped to 0 to 1 or 1 to 0 to see that whether that property can be violated.
He's also asking, does the framework allow for multiple bit flips or only a single line?
Yes, it allows for multiple bit flip. But for feasibility analysis right now, for a small design, we have considered all of the combinations of target cells. But for larger designs, so we have considered 2 concurrent fault locations at the same time. But you know that simulator, it allows multiple fault simulation.
All right, let's take one more question due to time limitation. Do you validate theoretical faults by implementing a real physical attack, or is everything simulated?
Right now, everything is simulated, but one of my students is writing, it's working on validating on FPGA, and we could actually show one of the properties right now, but we haven't tried the rest because it's ongoing at home. But that's part of our plan, definitely, to validate all of our results using FPGAs. And it's possible at A6 right now, but FPGA is a more practical way to do it.
All right. Thank you very much, Farimah, for this amazing webinar. Guys, this Friday we will have another webinar on automotive product security, and you can find more details about it and you can register on our website, and you can also find the registration link in the Zoom chat box. Please don't forget to fill in the feedback form and share your experience with us. It would also be good if you would give a shout out to Farimah on social media. And thank you once again, and hope to see you this Friday. Have a nice evening.